Hi, everyone. So welcome to Project Jigsaw Under the Hood. My name is Alex Buckley. I'm in the Java Platform Group at Oracle. Just to say, this is a 45-minute presentation with 55 slides. So I'm going to go speedily through them. I would like to not take questions, if possible, during this session. There is a workshop at 4:30, I think it is, where Mark Reinhold, who is over there, and I guess Alan Bateman will answer everything you ever wanted to know and all the things you don't about Jigsaw. So it will be good if, I'm sure you'll have questions, especially you, but if you could hold them until the end, that would be great. So, Jigsaw Under the Hood. In JDK 9, the main feature is a module system that lets code be more reliable and maintainable. We've used the module system to turn the monolithic JDK into the modular JDK, breaking up the rt.jar file, as you've heard, inside the JDK into dozens of reusable modules. JDK 9 also has small enhancements to the Java language and somewhat larger enhancements to the standard libraries. Plus, Javadoc gets a search box, and the JDK includes a REPL at last. Project Jigsaw is a project led by Oracle in OpenJDK. It's the container for all of our work building a module system and modularizing the JDK. We're standardizing the module system in the Java community process through JSR 376. We're also standardizing the structure of the modular JDK in the Java community process through the umbrella JSR for Java SE9. When you use JDK 9, you're always subject to the rules of the module system. That's what's under the hood, and it's what most of this talk is about, though I'll touch on some aspects of the modular JDK near the end. The talk has 4 parts. The first part explains how the module system works with the Java language and VM to improve reliability of your code. The second part is about migrating to modules. The third part explains what the module system is fundamentally capable of beyond what you can express in the language and VM, in the language. And the fourth part is about preparing to run on JDK 9 and how frameworks can take advantage of the module system. So part 1. Everyone knows the hierarchy of accessibility in the Java language and VM. It's simple to understand, easy to use, and strongly enforced by the compiler and VM. But it has a big weakness. The only way to share code between packages is with public, but then you're sharing with everyone. It's not surprising that package friendship, in one form or another, has been requested many times over the years. One goal of the module system is strong encapsulation, to allow a component to declare which of its public types are accessible to other components and which are not. The lines in italic are the levels of accessibility connected with the module system. Reading upwards, you can arrange for public types to be accessible only within their module, or accessible within their module and to specific other modules, or accessible to everyone. Now, as usual, migration drives a lot of our thinking. We want to make it easy to place an existing package into a module and immediately give that package the benefit of strong encapsulation. We don't want each and every public type in a package to have to opt in to strong encapsulation. So public types in a package are not accessible outside their module by default. That is, public on a type declaration no longer means everyone can access the type. What happens if someone tries to access a public type that's not accessible? Here's an example from Glassfish 4.1. To be fair, this is a few months old now, so it may have been fixed. At the time, Glassfish 4.1 didn't start on JDK 9 because the VM throws an illegal access error. The error message is, class com/sun enterprise security provider policy wrapper in Unnamed Module, don't worry about that yet, cannot access class sun security provider policy file in module Java base. The point is that the class sun security provider policy file is declared public. But since it's a JDK internal API, it's now accessible only within the Java base module. Sorry, Glassfish, you need to find an alternative API. In JDK 9, modules are first-class program components like classes and interfaces. Here is the Java declaration of the java.sql module that contains JDBC. It's in a file called moduleinfo.java in a directory named after the module, source JavaSQL. The compiler treats it like any other Java file and translates it to moduleinfo.class, which you can put in a jar file as normal. We call that a modular jar. The package hierarchy exists in the same directory underneath source JavaSQL. So moduleinfo.java is outside all of the packages in the module. And it's the job of the module declaration to say whether a package in a module is strongly encapsulated or not. It's easy to get strong encapsulation. Don't mention the package in the module declaration. To allow other modules to access the package, or more specifically the public types in the package, add an exports clause. You can export to all other modules, or you can say exports to give access to only your friend modules. So to be clear, module java.sql, that's the module name. The exports clauses are naming packages. They're naming packages. They just have similar syntax. At compile time, JavaC prevents code outside this JavaSQL module from accessing any packages except for those listed. You get the same compile time error as when you try to access a package private type from outside its package. At runtime, the VM throws an illegal access error like you saw with Glassfish. Let's look at the VM more deeply. Traditionally, accessibility in the Java platform is about who is doing the access and what is the public protected private flag of the target class, the one you're trying to access. At runtime, the VM uses the class loader of the accessing class to find and load the target class, and then the VM checks the flags on that target class. Now, because the VM relies on class loaders, people can create loaders that only know how to find and load classes of certain packages. In effect, loaders can isolate one package from another. In the top picture, class p.c is trying to access class q.d. The loader for p.c knows to delegate to some other loader for any class in package q, such as q.d. Only when that other loader has loaded q.d can the VM check its flags to see if p.c can access it. In the bottom picture, the loader for p.c has been set up to have no idea where to find package q, so no access to q.d is possible from p.c. Now, technically, this isn't a failure of accessibility because the VM never gets to check the flags of q.d. Instead, it's a failure of visibility. q.d is invisible to p.c by reason of class loader delegation. But the effect is still quite powerful. If the class loader of the accessing class, p.c, can't find and load the target class, then it doesn't matter if the target class is public. It's effectively encapsulated. Whoever sets up the class loaders sets up the encapsulation. But encapsulation based on class loaders is not strong encapsulation, sad face. Yes, sad face. It relies on packages being carefully apportioned into different loaders. But that isn't how the JDK has traditionally worked. Most code in the JDK is loaded by the bootstrap loader, while code on the class path is loaded by the application loader. And spinning up lots of loaders for all of that code would be, you'd have compatibility side effects like you wouldn't believe. And in any case, with multiple loaders, or lots of loaders, there's no actual isolation. You can circumvent class loaders by getting hold of references to Javaland class objects. And once you have a class object, the loaders are they're irrelevant. And it's impossible to stop references to class objects from being passed around. So strong encapsulation is about being able to prevent access, even if the accessing class and the target class are in the same class loader, and even if someone is using core reflection to manipulate class objects. Let's assume that multiple modules are somehow mapped to the same class loader. Can class p.c in module X access class q.d in module Y? Now, another goal of the module system is reliable dependencies, to replace the brittle, error-prone class path mechanism with a means for program components, modules, to declare explicit dependencies on one another. In order for P.C to access Q.D, not only does module Y need to export package Q, but module X needs to explicitly depend on module Y. The formal name for depends on is readability. Readability underpins accessibility in the Java language and VM. The accessing class P.C must be in a module that reads the module of the target class, module Y, and the module containing the target class, module Y, must export its package, Q, to at least the module of the accessing class. So you can see that accessibility is a two-way street. Module X reads module Y, and module Y exports package Q to at least module X. Note here that accessibility is independent of class loaders, just like before the module system. This is important for two reasons. It means accessibility works at compile time when there aren't any class loaders, and it means you can reason about accessibility based solely on requires and exports clauses in moduleinfo.java. There's no need to worry about what class loaders may or may not be in existence at runtime. So in fact, the exports part of accessibility is quite straightforward. A package is either exported or it isn't. But on readability, there's more to say. When you depend on a module, you depend on a hopefully coherent set of packages that it exports. In some sense, those packages are the interface of the module. Inside the module, hundreds more packages may sit, strongly encapsulated, waiting to help implement the interface. And more than that, when you depend on a module, you indirectly depend on all the modules it depends on. For example, if you depend on the java.activation module in the JDK with its 35 classes, then you also depend on the java.desktop module with its 5,835 classes. If the watchword for JDK 8 was functional, the watchword for JDK 9 is transitive. You should think in terms of the set of modules needed, whether you like it or not, frankly, transitively by your application. And those indirect dependencies can be as important as the direct dependencies. So let me show you how readability handles that. This is an example of readability from the graph of JDK modules. The Java SQL module on the left that holds JDBC requires the Java logging module that exports the package Java util logging. This lets code in the Java SQL module access the public types of Java util logging, such as logger. You can see that some code in the JDBC driver manager class is newing an instance of logger. What if the API of the Java SQL module, rather than its implementation, wants to use the logger type? For example, the JDBC driver interface has logger in a return type position. Let's look at this through the eyes of an application module that uses JDBC, MyApp. In order to use that driver method that returns a logger, the MyApp module not only needs to read the Java SQL module, but also the Java logging module, which exports that logger type. It will be a pain if the developer of MyApp at the top had to remember to say requires Java logging when using the API of Java SQL. Sad face. MyApp has to remember to write that. The good news is that the Java SQL module can take on the responsibility of remembering. Look at the Java SQL module now. It says requires public Java logging. The word public here means that anyone who reads the Java SQL module also reads the Java logging module for free. The MyApp module, which reads Java SQL, doesn't have to bother with requires Java logging because it reads Java logging thanks to reading Java SQL. Happy face, cross out requires Java logging. This is called implied readability, and it's very powerful. It's powerful because it lets a module be refactored without breaking its consumers. For example, suppose that the Java logging module has some auxiliary packages that we'd like to start shipping in a separate module, log extras. The Java logging module can say requires public log extras, so that my app, up at the top, maybe many levels further up, my app, which implicitly reads Java logging, thanks to reading Java SQL, also implicitly reads log extras. My app will be unaware that this refactoring is happening. So the readability module supports downward decomposition. Any module you read can be decomposed into new modules, and readability of those new modules can be recovered with a requires public clause in the old module. You can see that the definition of reads is recursive. A module X reads another module Y, either by requiring it directly, X requires Y, or by reading some third module Q, there's the recursion, where Q says requires public Y. And now that X reads Y, Y can say requires public Z, and now X reads Z. So you can keep on decomposing all the way down and not affect the consumers. Now be careful. Once people require your module explicitly, you can refactor it downwards as much as you like, but you can't delete it. There's no way for a module to stand in for another module by taking its name as an alias. If someone requires X and X is deleted, the module system won't start. Everything so far has been about accessibility in the Java language and VM, where the accessing class p.c and the target class q.d were known statically, constant pool. But accessibility extends to dynamic class references that you manipulate with the core reflection API, Java Lang Reflect. In this code, the parameter C is a reference to some class object. It's dynamic. We can't control what class object is referred to by C at runtime. Maybe it's a class object representing a private class, private nested class, of an unexported package of an unreadable module. That is a class object that very deeply represents an inaccessible class. Similarly, we can't control what MS refers to. Maybe it's private methods of that inaccessible class. We want to ensure strong encapsulation, even when core reflection is used to access types and their members. The only opportunity to do this is when an operation like new instance is performed on a class object, or get on a Java Lang Reflect field, or invoke on a Java Lang Reflect method. These operations now perform the same pair of checks as the compiler and VM. Does the caller module read the target module, and does the target module export the relevant package to the caller module? Now, in core reflection, for convenience, the answer to the first question is always yes. The caller module is just assumed to always read the target module. This is because a module can always choose to read more modules at runtime by reflecting on itself. So there's no point making the caller module do that dance to reflect every time. So core reflection works as if every module reads every other module. In contrast, the module system API does not allow a module to augment the exports of another module. A module can only augment its own exports, and if it didn't, you can't reflect your way into it. Even setAccessible respects strong encapsulation. Suppose you have a Java Lang Reflect field that represents a private field of a public class, sounds good so far, but that public class is in a package that's not exported. setAccessible true will fail. It can't manipulate the accessibility of anything in a non-exported package. Just like the get method of Java Lang Reflect field, setAccessible performs the same pair of checks logically performs the same pair of checks as the compiler and VM. Does the caller module read the target module? And does the target module export the relevant package to the caller module? Again, the answer is yes for the reading part, for convenience. So it comes down to whether the target module exports the package in order for setAccessible true to succeed. That's accessibility and readability. You have questions, I understand. Let's talk about them at the workshop. It used to be a simple check. It was public or same package. Leave out protected, it's a nightmare. In 9, the accessibility is used to strongly encapsulate module internals, and the accessibility relies on the readability relations between modules, which can be direct or implied. And this accessibility fundamentally is enforced at compile time, runtime, and reflection. So, different kinds of modules. Everything so far has been about named modules, modules explicitly declared with a name in moduleinfo.java. What about jar files on the class path that don't have a moduleinfo.class file? They seem to be in a world of their own. To keep the model of accessibility and readability consistent, we introduced the unnamed module. All classes not in named modules are in the unnamed module. It's as if, watch the left, everything on the class path is in one big module. Because it's a module, we can ask two questions. What does it read, and what does it export? What it reads is simple. Every named module, all of them, as if by magic, for free. There's an asterisk after that. We can talk about that as well. This means that anything exported by a named module can be accessed by the unnamed module. You can turn a jar file into a named module by adding moduleinfo.class and putting that jar on the module path where named modules are found. Jars left on the class path will not realize anything has happened because they're reading for free that named module you just made. That's a huge help for migration. The next question is what the unnamed module exports. Before that, though, we should ask, who reads that unnamed module? Now, remember, our goal in the module system is reliable dependencies. We believe very strongly that named modules, whether in the JDK or outside the JDK, should not read the unnamed module out of the box. It would make a mockery of reliable dependencies to let named modules depend on the arbitrary content of the class path. So you cannot write requires unnamed or requires class path in moduleinfo.java. There are no reads edges going out to the unnamed module. Of course, this is a huge hindrance for migration because any jar you turn into a named module can't access the jars left on the class path. The answer is automatic modules. You can take a jar, say guava.jar, and move it from the class path to the module path. This turns the jar into an automatic module. That's all you have to do. An automatic module is a named module declared implicitly rather than explicitly. Its name is derived from the jar file name in obvious ways. Putting guava.jar on the module path gives an automatic module called guava. As before, whenever you see a module, you should ask, what does it read and what does it export? The automatic module guava reads everything in the JDK and the unnamed module. It's as if it says requires unnamed. Now the hindrance to migration is gone. You can turn a jar into an automatic module, and it can still access the jars left on the class path. We asked earlier what the unnamed module exports. The answer is all its packages, all the packages in junit.jar and glassfish.jar and hibernate.jar, precisely to help code in automatic modules which read the unnamed module. There's the arrow going out to it. And because an automatic module is a real named module, another named module can require it. So suppose the myapp module from before says requires guava. So there's a reads edge from myapp to guava. What does an automatic module like guava export? That's easy, all of its packages. So myapp can access all the public guava types. Myapp could even say requires public guava to transmit its dependency on guava up to its own consumers, so that anyone who reads myapp would read guava for free. So by moving a jar from the class path to the module path, you get an automatic module that lets you start building up your own graph of modules. It's not necessary to wait for every jar on the class path to be modularized by its author before you start developing modules like myapp that require it. So there are three kinds of modules: explicit named modules like java.sql, automatic named modules like guava, and the unnamed module, aka the class path. And you can see there's lots of readability for free to help with migration. Part 3. I said before that strong encapsulation is independent of class loaders, and if I didn't, pretend I did. This means that the model of class loading in JDK 9 is unchanged. The mechanism of loader constraints is unchanged. The notion of runtime packages is unchanged. The Java-Lang class loader API is essentially unchanged. In addition, the actual class loaders in JDK 9 are unchanged from JDK 8. There is a bootstrap loader. There is a platform loader, renamed from extension. And there is the application loader, some people call system, not me. Traditionally, the vast majority of JDK classes were defined by the bootstrap loader. And indeed, critical JDK modules, such as java.base, still have their classes defined by the bootstrap loader. For non-critical JDK modules, it's important for security to move their classes out of the bootstrap loader. Modules in the bootstrap loader run with all permissions, which is not ideal from a security perspective. And they can only be deprivileged, that is, run with fewer permissions, if they're not defined by the bootstrap loader. So in JDK 9, all the modules containing Java EE technologies, such as java.corba, have been moved out of the bootstrap loader, as well as the JDBC modules, Java SQL and Java SQL Rosette. Their classes, they're all defined by the platform loader. Frankly, moving a module as big as Java Corba, 1,831 classes and 31 exported packages, is no small accomplishment. The deprivileging work of minimizing the permissions, that will continue for many years. Now, the application loader is then responsible for everything else. A number of JDK tool modules, such as JDK compiler, have their classes defined by the app loader. All classes in modules on the module path, whether they're in a modular jar or in an automatic module, like Guava from before, are defined by the application loader. All classes on the class path in traditional jar files like junit.jar and glassfish.jar are defined by the application loader. So very little, in some ways, has changed. But there are a couple of things to say about compatibility. First, frameworks that delegate directly to the bootstrap loader to find JDK classes might break on JDK 9, because many JDK classes aren't there anymore. Frameworks should use the new class loader method, getPlatformClassLoader, which returns a loader guaranteed to provide visibility of exported JDK classes. Second, the application loader is no longer an instance of URL class loader. Frameworks that assume it is, in order to hack into its addURL method, will break on JDK 9. The only supported way to dynamically extend the class path is with the class path attribute in jar files or with the agent API in Java-Lang instrument. Now, you may be wondering where the module system itself lives in all of this. It's important to realize where the module system isn't. Traditionally, a module system was simply Java code that acted as a factory for class loaders. There it is, Java code in the app loader. It created loaders that defined classes found in modular artifacts, and the loaders delegated to each other in accordance with some kind of modular imports and exports. As I mentioned before, there is some encapsulation of classes there because the loaders can hide classes from each other. A module system that does this will still work on JDK 9 because class loading hasn't changed. But the module system in JDK 9 is quite different. The module system in JDK 9 is not a factory for class loaders, but rather a conduit that allows modules to be communicated to the VM. Whoever creates the class loaders is responsible for using the module system API to transmit module names, contents, dependencies, and exports down to the VM. That's how the VM knows enough to enforce accessibility. It's also how the core reflection API can enforce accessibility, since it's based on VM-provided class objects. You can think of the Java launcher as creating 3 loaders and doing that transmission for modules on the module path. You can see why we wanted the module system to be disinterested in class loaders. The JDK has been factored into dozens of modules, but its 3-class loader architecture hasn't changed. Encapsulation is provided by true VM-level accessibility, not by class loader-based visibility. So the module system doesn't need to mandate 1 loader per module. It can handle multiple modules per loader just fine. You'll recall I talked earlier about the unnamed module as a vehicle for compatibility. Strictly speaking, I was referring to the unnamed module of the application loader. Every class loader actually has an unnamed module. If the VM sees a class being defined by a loader, and the VM can't associate that class with a named module that was transmitted earlier, the VM treats the class as being in the loader's unnamed module. And as you might guess, the VM always allows access to public classes in an unnamed module. Everything works as before. So this all means that every class actually is a member of a module. Even classes in jar files on the class path, in red, are members of a module. That's the seventh blue box in the VM on the right. It's the unnamed module of the app loader. So if you have a class object, the getModule method will always return a Java Lang reflect module object. The module system introduces the concept of a layer to associate loaders with modules. A layer is a family of class loaders that together serve to load classes for a graph of modules. Logically, the Java launcher defines the boot layer consisting of the three familiar loaders. It's the boot layer that associates the Java base and Java logging modules with the Bootstrap loader, Java SQL and Java Core with the platform loader, and so on. A layer is created from two things, a graph of modules and a function that maps modules to loaders. On the left is the graph from resolving the JDK JLink module, which contains the JLink tool for building runtime JDK images. On the right is a Lambda expression mapping modules to the Bootstrap loader and the application loader. Creating a layer informs the module system about the packages that will exist in the program and the modules they'll come from. The module system passes this information to the VM so that when classes are eventually loaded and defined, the VM knows which module a class belongs to and what that module reads and exports. It's like the VM has a shadow copy of the module graph that it uses when checking accessibility between classes. Now, because of how class loading works, which hasn't changed, the module system must enforce certain constraints on a layer's module graph and on the layer's mapping from modules to loaders. Let's talk about the graph first. This is the graph of modules in JDK 9. The main thing to notice is that it has no cycles. This is the first and biggest constraint on a module graph. It's taken almost a decade to detangle the tens of thousands of classes in the JDK to the acyclic and relatively sane state you see here. We'd like to keep it that way. In fact, one of the motivations for investing in modularization of a code base is the knowledge that once complete, there won't be any backsliding into the ball of mud that cyclic dependencies allow. The second constraint on the module graph is that a module must read only one module that exports a package P. If a module could read more than one package, if a module could read more than one module that exports P, as X is trying to do here, X is trying to read Y that exports P and also trying to read Z which exports P, in which module would P be accessed? Really, there's no answer. The module graph is just broken. So we defend against that. Only module graphs which obey this constraint, top line, and have no cycles can be turned into a layer. That's really what we mean by reliable dependencies. Dependencies are reliable when a module can access only one version of a package at a time. There are no split packages like you get when multiple jars on the class path contain potentially different versions of the same package. Now you might wonder if it's possible for X to read version 1 of module Y, while at the same time another module reads version 2 of module Y. After all, X and the other module would each read their own version of Y. They'd each read only one module exporting P. The answer is that it's not possible because it would only work safely in certain scenarios, and outside those scenarios, it's not clear that supporting it out of the box, which is to say in the boot layer with the Java launcher and supporting the Java compiler, is worthwhile. But that's certainly something we can talk about. Recall that a layer includes a module graph, for which we saw two constraints, and a mapping from modules to loaders. The main constraint on the mapping is that if different modules in the graph have a class called C, then those modules must be mapped to different loaders. Perhaps these different modules in the graph have the same internal packages, so they must go in different loaders. Actually, more conservatively, we say that if different modules in the graph have the same package, not just the same class, they must be mapped to different loaders. The mapping from modules to loaders has one more constraint that's not practical to check because it concerns how loaders behave at runtime, but we expect class loader authors to obey it anyway. It's that loaders must delegate to each other in accordance with the reads edges of the module graph. The reason is obvious. If module X reads module Y, then in order for X's classes in one loader to access Y's classes in another loader, X's loader must delegate to Y's loader. You now know enough about named modules, unnamed modules, module graphs, and layers to appreciate an exquisite interaction between JDK code in modules and badly behaved jars on the class path. But there isn't time in the session to go through it, so please come to our workshop today to hear about it. As their name suggests, layers can be layered. When a graph of modules is resolved, it's actually resolved against a parent layer. Then when the graph helps to create a new layer, that new layer picks up the parent layer. This allows a graph of modules to have dangling references, that is, requires clauses for modules that the module system will find in a parent layer during resolution. On the left, resolution has set up not only a reads edge between modules in one layer, but also a reads edge between modules in different layers. Now, constructing a tree of layers in this fashion is the job of a framework. And layers give frameworks tremendous freedom to organize modules at runtime without upsetting the framework's traditional uses of class loaders. It's like Invoke Dynamic. It's a way for framework developers to interact with the VM to reify information about the shape of a program. And so one scenario where layers help out is supporting multiple versions of modules. Here, a framework like an app server has created two layers on top of the boot layer. On the left, the Hadoop layer reifies a module graph with Guava version 11 and Jackson version 1. On the right, the JavaScript layer reifies a module graph with Guava version 18 and Jackson version 2. Each module graph is well-formed and mapped to loaders in a sensible way. But the modules in the Hadoop layer are not aware of the modules in the JavaScript layer and vice versa. But note, this is all thanks to a framework creating the Hadoop and JavaScript layers. The Java launcher doesn't create layers like this. All it does is resolve the module you give on the command line, then map everything in the resulting graph to the application loader of the boot layer. It supports only one version of each module. And the reason is to avoid the nightmarish problems that occur when multiple versions of a module casually come into contact with each other. It's really only safe to use multiple versions of a module when a framework like an app server is in control. So just as modules wrap up coherent sets of packages and interact with the VM's accessibility mechanism, layers wrap up coherent sets of modules and interact with the class loader visibility mechanism. They're a higher layer thing. It'll be up to frameworks to make use of layers in the next 20 years, just as they made use of class loaders in the first 20 years. I urge framework developers to open the JDK9 Java doc and look at Java Lang module configuration and Java Lang reflect layer. So that was a deep dive into loaders and layers. Modules do a better job of encapsulation than loaders, but loaders are still necessary. Layers control the relationship between modules and loaders. And assuming class loaders respect the module graph, the system is safe by construction, no cycles or split packages. Zooming all the way out, we have strong encapsulation of modules by the compiler, VM, and core reflection. There are unnamed and automatic modules to help with migration, and the system is safe by construction, no cycles or split packages. There's still a long road ahead. Although the module system is conceptually simple, there are changes in JDK9 that probably won't break user code, but might break framework code. I'd like to go through them quickly. There are 3 areas of incompatibility in JDK 9 connected with Java SE, the platform. First, we've removed 6 methods from the packages Java util logging and Java util jar. Their signatures made the Java base module depend on the Java desktop module, and no one wants that. This removal was announced in the Umbrella JSR for SE8 in 2014. In addition, we've removed 2 AWT packages that were never supported despite being in the java.star package namespace. Second, the Java EE types shipped with the JDK are not accessible by default. This means Corba, JAX-B, JAX-WS, the Java Activation Framework, and the JDK's subsets of the Java Transaction API and the Common Annotations API. The types are physically in the JDK image, but the modules are not read by the unnamed module out of the box. If you're writing a module, if you're declaring a named module yourself, no problem. Just require Java Corba or require Java XML bind, whatever. But if you're running code from the class path, you need a command line flag to activate the EE modules. Third, the version strings reported by system properties have changed. Code that looks for 1 dot at the beginning of the string will fail on JDK 9. That's not a module system feature, but I bring it up because you get system properties through a Java SE API, and it's a very, very visible thing. There are 3 areas of incompatibility within the JDK implementation. First, we've slimmed down the sunmisc package. Sunmisc unsafe is still accessible, but sunmisc base64 encoder and base64 decoder are gone. One thing you can do is run the JDEPS tool, which came with JDK 8 over all your jars. It'll tell you if you're using unofficial classes like sunmisc base64 encoder and recommend official replacements like the Java util base64 class introduced in JDK 8. Second, many JDK internal APIs are not exported. Code that tries to access types in the sun net www package, or sun security x509, or comsun org apache xerxes internal jax-p. You laugh, we meet these people. Will fail with an illegal access error. The only way to regain access is with a command line flag. Third, many internal aspects of the JDK have been overhauled, such as the layout on disk and the implementation of the 3 class loaders. Code that assumes there's a file called rt.jar or tools.jar in a particular directory will fail on JDK 9. Scripts that try to patch the JDK with -x boot class path /p will fail on JDK 9. I mentioned before, code that assumes the application loader is a URL class loader, or that assumes all JDK classes are defined by the bootstrap loader, will fail on JDK 9. The module system tries hard to support migration, but it takes only 1 unmaintained library to prevent migration to JDK 9. If that library won't run on JDK 9, nor can anything on top of it. Please don't be that library. Very quickly, if you own a framework and it doesn't touch anything I just mentioned, which frankly it shouldn't, it should work out of the box on JDK 9. Suppose the framework is loaded by the application loader, and it creates its own loaders that subsequently load scripts, plugins, classes, what have you. Recall there's an unnamed module in every class loader. The application loader has an unnamed module, and any loader you create has its own unnamed module. All these unnamed modules read each other, and they export all of their packages to everyone. They're real modules. You can even label them so they appear nicely in stack traces alongside classes from named modules like Java Base. So the framework starts off in the unnamed module of one loader. The classes it operates on are probably in unnamed modules of other loaders. Any dependencies of those classes are probably in the unnamed module of some other useful loader. That's the modularized nothing stage. The next thing you can do is to modularize your framework. That is, you deliver it as a named module that's put on the module path. Being a named module lets you strongly encapsulate its internals and express dependencies on JDK modules. Ultimately, the framework can be linked into the JDK image. As for the classes it operates on, they can still come from the class path and be loaded by the same loaders into unnamed modules. That's the modularize the framework option. An alternate next stage is for the framework, it's accept modular inputs, the one at the bottom. It's for the framework to continue on the class path and live in the unnamed module of the application loader, but to accept modular input, that is to introspect on classes in named modules. The classes might be in the JDK image or in modular jar files on the module path. Ultimately, the classes in these named modules are loaded by the application loader or its parent, so they're visible to the framework. And as long as that named module exports some packages, the framework can access them to do whatever it needs to do. The final stage modularizes the framework and the classes it operates on. This means everything can be linked into a JDK image, and the classes being operated on, and the classes generated by the framework can be strongly encapsulated. The Nashorn talk next will discuss generating classes that support a language implementation, which no one can access except the framework module. You don't have to change your class loader hierarchy in any way, just to find modules at runtime to contain the private classes and associate them with your existing loaders via a layer. Last slide. The single best thing you can do to prepare for JDK 9 actually is run the JDEPS tool, which analyzes dependencies. It'll tell you if your code or code you rely on, anywhere on the class path, will be affected by changes in JDK 9. Also, please try the JDK 9 early access binaries on java.net. The module system has been present and active in these binaries since March 2016. Everything you ever wanted to know about the module system is discussed in JEP 261. I cannot emphasize enough how much valuable information lives in JEP 261. There's also JEP 260, which defines JDK internal classes which are nevertheless exposed in JDK 9. JEP 223, which describes the new version strings that begin 9 dots. And JEP 220, which describes how rt.jar has gone away. Finally, JEP 200 gives an overview of the JDK modules. But if you've already read JEP 261, please read JEP 261. I promise you the answers you seek are there. There won't be any surprises from seeing the JDK module graph. And with that, only slightly over time, thank you very much.